Okay, there we go. Okay, so thanks for the reminder. I got a chat message um, saying or asking if there's another midterm coming up, and so actually I'll just mute here. There we go. And so that caused me to look at your syllabus and remind myself when your last midterm is, and so it's scheduled for April 21st. And so pretty well whatever we get done this week will be the cutoff for the exam. And so I'll post a practice midterm homework assignment next Monday, so you can work on that and prep for the next midterm. I have to say, uh, in all the years I've taught Chem 131, the second midterm is always the worst average because you've got limiting reagents, you've got a lot of stuff going on, and this last exam is one of the highest averages, and so people can kind of get their minds around Lewis structures and that kind of stuff pretty easily. So yeah, I guess something to look forward to. Maybe a average booster here coming up. Okay. All right, so we are going to start a really key chapter. So I think, there's really two key chapters in this whole class. It's the one on moles, grams, that one, because it goes into empirical formulae and all that. This is maybe the most important chapter, maybe of all of your introductory chemistry classes. So I think even more than 132, just because what we're going to talk about in this chapter is so key for virtually any application. So, you want to talk about, how the vaccine is going to work when they come up for this cure for COVID-19. It is going to deal with intermolecular forces that are based on molecular structures. So, really, this fundamental that we're going to talk about in this chapter. Okay, so a lot of chemistry can be boiled down kind of to what we're going to lay the foundation on here. Okay, so this is going to involve really talking about bonding. So this chapter is going to describe bonding theory, and in particular, we're going to talk about covalent bonding. Okay, and so covalent bonds means sharing of electrons. Okay, and so you can think of really the two extremes of bonding. You've got ionic and covalent. Okay, and so ionic is between a metal and a nonmetal, versus covalent are between two nonmetals. Okay, and so remember in the periodic table, the metals are all on the left-hand side. So we're talking here about, like groups 1 and 2 pretty well. With nonmetals are, really the group, I don't know, typically it's group 15 to 17. Okay, something like that. So, halogens, the chalcogenides, those groups. Okay, and so in practice, this is where there's absolutely zero sharing of electrons, and this is sharing. Okay, and in practice, there is really no such thing as, even ionic. There's really no such thing as 100% ionic. There's always some amount of covalency or sharing of electrons, even in ionic compounds. Okay, but by it's something like maybe in sodium chloride, for instance. It's probably 98% or 99% ionic or something like that. But if you get into compounds like beryllium chloride, this is a group 2. Okay, so you'd expect it to be ionic. It's actually has a lot of covalency in this, and so it's um, I don't know, probably like more than 50% covalent bonding in this. Okay, so uh, beryllium is kind of an exception in the group twos. It tends to be, more covalent in its bonding. Everything below that, like magnesium, calcium, those are, leaned more toward ionic. Okay, and so it's probably TMI really, or maybe off on a tangent or something. But I just want to bring that to your attention that when we talk about covalent and ionic, compounds are typically somewhere in the middle, okay, or they're leaned on one side where it's predominantly covalent, for instance. Okay, all right, so you have this sharing of electrons in a covalent bond, and so this is just an illustration of your two bonds. You've got your nucleus, positive nucleus in the middle of these two atoms, and then you've got the electron cloud. So this is kind of looks like an s orbital here, for instance, okay, where your electrons are all located. And so you've got the repulsive effects between these two positive nuclei, okay, and then you've got the attractive effects between the electrons of this atom, we'll say, and the positive nucleus of the other atom, okay, and so in forming the length of this, so how long is this bond length here? It's really just minimizing the repulsions and optimizing the attractions, okay? And so this is what that looks like, okay? So we have energy going up here, and so as energy goes up, we would say that it is becoming less stable, okay? And what happens, I guess these are the two scenarios where you've got, two atoms, and you can bring these closer to each other. Okay, so if we kind of, maybe start here at this line here, where it's kind of like zero energy, and we push these hydrogen atoms closer and closer together, you can see that you're going to really destabilize the molecule because you're going to just really have strong repulsions amongst the positively charged nuclei. Okay, so you've got this and this, and if you really push them close together here, these are going to really repel each other, and it's going to shoot up the energy exponentially. Okay, so it's really not going to prefer this. And so kind of starting from this, if you move them farther and farther away, you're going to reach a minimum. Okay, and so this is the lowest point in the energy profile, and this is what we call bond length is. Okay, and so this is 74 picometers in this particular case for two hydrogen molecule, or H2. Okay, and so that is the most stable energy. That is the sometimes called the internuclear bond length. Okay, so let me write that down. Internuclear bond length. Okay, and then as we move these hydrogen atoms even farther away from one another, now the energy goes up again. Okay, and so now the attractions are really too weak between electrons of one atom and the protons in the nucleus of the other atom. And so the energy now goes up. And you'll see it will kind of reach this line where it kind of stops. And so at this point, this is where we have now broken this bond. And so at this point, there's no bonding. Okay, so this is really called between this point. I guess I can't draw on here, can I? Let's see. Let me see. Animation. No. There it is. Okay. So between this point and this point, Okay, so this distance here, okay, is called the there we go, the bond dissociation energy. Okay, so that is how much energy do I need to hit, in this case, a hydrogen molecule with to break it apart. Okay, so when you're at this point, you say that there's really no molecule anymore, so we have broken the bond. Okay, so at this point, you're breaking, you're moving the atoms away, but it'll reach this point where you've now broken it into two separate atoms. So we really consider this really two separate atoms, whereas this is the molecule. Okay. All right. So any questions about that so far? Okay. All right. Oh, there we go. Okay, so these are values. So the bond dissociation energies for various types of bonds. You will never have to memorize these. It's just, so you'll be given these values. I guess something to point out is that triple bonds are typically have more energy than double bonds, okay, and then double bonds have more energy than single bonds, okay. And so as far as these bond dissociation energies, a single bond is typically less than a double bond, and it's less than a triple bond. Okay, and you can think about it, I guess that kind of makes sense, right? Because here you've got two electrons that serve as the glue between these two atoms. In this case, you've got 4 electrons in between them. Here you have 6 electrons, right? So each of these lines, I guess we haven't talked Lewis structures yet, but each of these lines indicate 2 electrons, okay? All right, so and it also has to do with size of atoms as well. So an HH is pretty strong, right? Even stronger than a CH because these atoms are really, really small. So they've got overlap of really, really small 1s orbitals. And so they can approach each other pretty closely and overlap really strongly. And so that gives rise to a stronger bond, okay? And these are a little bit larger orbitals, okay? So they can't approach each other as closely, so the bond strength is a little less, okay? All right, so some properties of these, really what you're going to notice, covalent versus ionic, it really doesn't have much to do with these two. So the formula mass or the appearance, physical appearance. So sometimes you'll get covalent compounds that are gases, liquids, or solids. Ionic compounds will mainly be solids. Although you could have some liquids as well for these. So there's something that's called ionic liquids that are used, let's say in batteries or those types of things. But really where you're going to see the difference between ionic and covalent is really with these two. So the melting points and the boiling points. And so look at the difference here between, sodium chloride, for instance, has a melting point of 800 degrees. HCl is, below 0 degrees, right? Because it's a gas, so it's minus 115. And so the melting points of ionic compounds are much larger than covalent compounds. Okay? And so we're going to talk about that kind of in the next chapter when we get into energies. We're going to talk about that a little bit more, like what's involved in forming and then breaking apart ionic compounds. For ionic compounds, there's something called the lattice energy. Okay, and that's, how much energy does it take to break apart an ionic compound? And so in ionic compounds, really, you are just breaking apart these ions, right? So you don't have any electrons between them, and so the only thing that you have are these electrostatic repulsion or attractions between a positive ion and a negative ion. Okay, and so um, as you'd imagine, the lattice energy would go up depending on the sizes of the ions and the charges too. So for instance, if you have this, that's going to have a larger lattice energy because now you've got something that's even more positive that's attracting the negative. Okay, and so we'll get into that, in another chapter a little bit more. Um, but yeah, typically these melting points, they can go even up into the thousands for some of these compounds for ionics, versus a lot of organic compounds, for instance, are covalent, and their melting points are in the hundreds at most. So maybe a couple hundred degrees Celsius is a really high melting point for an organic compound. Okay. All right. So when we're talking about covalent bonds, we have to get into a concept of electronegativity. And I think we've talked about this before. Electronegativity is really how strongly something is pulling electrons toward itself. Okay, and so if I draw a little kind of schematic of the periodic table, really rough schematic here, which is the most electronegative element in the periodic table? Any ideas?
Fluorine.
Yeah, fluorine. Yep. So up here, somewhere here, and I guess that's the noble gas. Okay, this is the most electronegative element in the periodic table, and the worst would be like, cesium, francium, something like that down here. Okay, and so electronegativity will increase as you go up a group and increase as you go left to right in a period. Okay, and so anything partnered with fluorine is going to be very polar. Okay, and so you can have these different ranges. So for a bond, you can have what's called a nonpolar covalent, and that means where the electrons are equally shared between these two atoms. And there are really only few examples of that. If you've got elements, like for instance this, so S8 is one of the allotropes of sulfur, and so you can have what is that? 4, 5, 6, 7, 8. Okay, so this is cyclooctasulfur. Okay, so in this case, you would say that each of these bonds, it's pretty equal sharing, right? Because it's the same atom on either side. And so if you were to take a snapshot of this bond, you would see that the electrons would be pretty well right in the middle, okay, between those two sulfur atoms, okay? And so if it's the case where you've got the same atom on either side, it's called nonpolar covalent bond, okay? And so, things like all those diatomics would have it, right? All these guys, etc. Okay, so that those would all be nonpolar covalents. But in practice, most of the time it's not, right? It's like this, for instance. And so now you've got two atoms that are different. And so this is called a polar covalent bond. Okay, this is. And so if you had to guess what atom in this molecule, so hydrogen chloride, Which atom is more electronegative? So, hydrogen is like way up here, and chlorine is right there.
Is it chlorine?
Yep, so chlorine lies closer to fluorine. Okay, so it's going to be more electronegative. Okay, and so we can indicate that two different ways. Okay, so this is more electronegative. And so we can say this. We can say that this end of the molecule, or the right end of the molecule, is going to have a partial negative charge. Okay, it's not okay to put it like this, just to say negative. Okay, because it's not ionic, right? It doesn't carry a full negative charge. But what you're saying is that since chlorine is more electronegative, the electrons will lie closer to chlorine. Okay, so now, if we take a snapshot of that bond, the electrons would be like here. Okay, so they would lie closer to the more electronegative atom. Okay, and so we say that this end would be kind of a delta negative, whereas this end would be a delta positive. Okay, because the electrons are moving in that direction. Okay, negatives, electrons are negatively charged. Okay, and so that's one way we can kind of indicate the the charge of this molecule, if you will, or the movement of electrons in the molecule. Another way is to indicate it with little dipoles. And so we would say this. Okay, and so this is another way to say that electrons are being moved. So this is called a bond dipole. Okay, and it always points to the more electronegative atom in the bond. Okay? And so we're going to use, I guess, these two different symbolisms a whole lot when we go into really the first topic in 132. So in the fall or whenever you choose to take it, you'll start to talk about intermolecular forces, like how do two of these molecules interact? Okay, and what you'll see is that, not surprisingly, if this is the positive end of this molecule, it's going to interact with the negative end of the next one. Okay, and so you can get these what are called intermolecular forces. Okay, which intermolecular means between two discrete molecules, versus a bond would be intramolecular force. Okay, or a bond, a covalent bond. Okay, so this kind of shows the two extremes, right? So this would be a nonpolar covalent where you've got equal sharing, and then you're moving here where there's now non-equal sharing of electrons. Okay, so you develop this partial charges. And then if you move to this extreme, now there's zero sharing of electrons. And now you've gone from a delta negative to a negative, right? Because there's no electrons between here. Okay. Does that make sense? Any questions here? No? Okay. And so just kind of showing how this looks like, or what this looks like, these are just some illustrations of electron density around the molecule. And so if you have a nonpolar covalent bond, this is just showing a neutral, I guess just equal sharing of electrons. You're not getting any buildup of electron density around one of the atoms versus the other. Okay, so it's kind of, you can see the electrons are just distributed evenly over this whole molecule. Okay, and you can see the darker green right in the middle. So the darker green just indicates more electrons. Okay, and so you've got a greater electron density right here. Okay. All right, so that's non-polar covalent. If we go to polar covalent, now you see, so the purple indicates less electron density, and so in HCl you can see that more electron density, so now you have red even, so that means a lot of electrons are centered more on the chlorine atom, okay? And then an ionic bond, you don't have any electrons really between them. So you just have full, you'd say in this case that all the electrons, I'll just mute for a second here. So all the electrons are on the chlorine. Okay, there's 0 electron density on the hydrogen, or on the sodium here. Okay. All right, so yeah, so you can calculate the dipole moment of a molecule. Okay, and that just means the difference in electronegativity between the two atoms in a bond. Okay, and it's one way to distinguish between if something is more polar than the other. Okay, so let's look at, these are the values. So again, something you won't have to memorize, okay? This would be one way to say, okay, is HCl more polar than, let's say, H2O? Okay, so which is more polar? Okay, and so you would just look at the difference in electronegativity between a chlorine and hydrogen. Okay, and so that would be chlorine is 3.0 and hydrogen is 2.1. Okay, so that's 0.9 difference. Versus here between an oxygen and a hydrogen, that's 3.5 minus 2.1. Okay, so that's, what is that, 1.4. Okay, so we would say water is more polar than hydrogen chloride. Okay, and so this is also one way to distinguish. So without these numbers, it's awfully hard to determine, what's more electronegative, oxygen or chlorine, because they kind of flank fluorine on either side, right? And so here you can see with numbers that oxygen is more electronegative than chlorine. Okay, and so
will we have to remember this chart?
You won't, no. So the ones I will tend, I could ask a question like this, where you actually calculate, and then I would have to give you these values, okay? But typically I will give a question like, which is more electronegative, silicon or oxygen, okay? And then for that, without these numbers, you would just look that, oxygen is higher and to the right of silicon, so that would be higher. Okay, so you're kind of just looking at, periodic trends to determine which is more electronegative. Does that make sense? Hopefully. Yeah.
Yes.
Yeah. Okay.
Yeah,
good.
it does. Yeah.
Yeah. Good. Okay. All right. So, pull out your cell phones or whatever you have, and let's go through some Chem 101s here. Okay. So this first one. So just a definition here. So a more electronegative atom or which one of these do you think? right. Yep, so this one, A, is correct. Yeah, so it's going to have more attraction. So this one had a little bit of popularity, so D. Um, an electronegative atom is likely to form an ionic bond with a highly electropositive atom. Okay, so remember, ionic bonds is a metal with a nonmetal. So let's say, it has a certain charges here. Okay, so this is going to be electropositive, which means that it loves to lose electrons, versus the nonmetal is going to be the electronegative, and that will like to gain electrons. Okay. All right. Okay, so that's covalent 1. Covalent 2. Okay. Which of the following is an example of a covalent bond? Okay, well, I guess we already used one in an example, so yeah. So C is the correct one here. Okay. What type of bonding do you have with these others here? So what would you say A is? What type of bond is that?
Ionic.
Yeah, so this is ionic. This one?
Ionic.
Yeah, ionic. What about this one? Aluminum, aluminum.
Polar, covalent. Polar.
No, it's actually another type that we haven't talked about, actually. So if you have, so a covalent is between two nonmetals. If you have two metals, whoops. So metal 1 and metal 2, whoops, you can't see that.
Is it an alloy?
It can be, yeah. So, yep, you could call it an alloy. That's a certain type of it. That, I guess, alloy would be a description of what type of compound. The bonding is called metallic. So it's a metallic bond. Okay. We will get more into that in Chemistry 132. Basically, what that looks like is all of these metals are electropositive. And so these are going to have a certain, different charges here. And so what happens is you will have a certain structure between these metal ions. And so, let's say you'll have like a cube structure or something like that. I'm a horrible artist, but I don't know if that even looks like a cube. But something like this, where you've got like a certain lattice with different metal ions here. And then you've got these what are called delocalized electrons that kind of migrate around this structure. Okay, and they're there to kind of, stabilize it. So these two metals have a positive charge, so they're going to want to repel one another. But these electrons kind of serve as the glue that kind of hold them in place. But they're not associated, this electron is not associated with one metal or the other, like they are in covalent bonding, right? And so, so they're free to migrate around the solid. And so that's why metals are really good electrical conductors, because if you put a charge on this solid, then you can move these electrons through the solid really easily, because they're not really tied together, between the different ions. And so it's kind of, without getting into a lot of details, I guess stay tuned. For Chem 132, we get more into metallic bonding. But yeah, that's the variety. If you have two metals, it's metallic. A metal and a nonmetal is ionic. And then two nonmetals is covalent. Yeah. Okay. Then covalent 3. Okay, the molecule NABR is yeah, and so sodium is in group 1 of the periodic table. And so that is classified as a metal. So here's something to keep in mind, actually, if I do my little illustration again here. Okay, whoops. Yeah, I guess. Okay, so hydrogen is above the other group 1s, right? Hydrogen, though, in bonding, that's why in some periodic tables you'll actually see, this is actually really weird, yeah, helium's here too, okay. But in some periodic tables you'll see hydrogen placed there above the group 17s, okay, because really in bonding, hydrogen acts like a nonmetal. Okay, in reactivity, how many electrons it likes to lose, etc. It shares those characteristics common to the group 1s, but really for bonding, consider it like a group 17. Okay, so that's why HCl was covalent. Okay, it had covalent bonding because that's a nonmetal, that's a nonmetal. Okay, so in this one, you've got a group 1, which is a metal with a nonmetal, so that's why it's ionic. Yeah, so A is correct. All right. And then covalent 4, last one of today, which is not an example of a covalent bond. Yeah, and so you're looking here for, and these, by the way, are very typical of questions you'll see on your next exam too. So really this easy. You're just looking for, if it's not an example, look for the one that has a metal in it. Okay, so you are correct. This would be ionic. Yeah. Magnesium nitride, let's say. Yeah. Okay. Again, we're kind of skipping this middle group as we generally do in general chemistry. The transition metals compounds, they really are a hybrid of covalent and ionic bonding. So it depends on what is attached to the metal. Those typically will have covalent bonding, and then it's more ionic between those substituents and the metal center. And so, yeah, so these are real hodgepodge or real mix of bonding. So the examples we're looking at are very clear cut. You've got a group 1 metal with nitrogen. On an exam, if you do get a transition metal like this, you'd still consider this mostly ionic, okay, because it still has a metal and a non-metal. Okay, it's just not as ionic as, for instance, NaCl or something. Okay. All right. So let's talk about, I guess, we're just going to set this up today, and then tomorrow we're going to go hardcore on this. Electron dot or Lewis structures. And so this is now really indicating how many electrons are involved in bonding. Okay, so Lewis structures will really show how electrons are involved in bonding between two non-metals. Okay, so Lewis structures can really only be drawn for covalent compounds, okay, or molecular compounds. Okay, so as far as semantics, when we say something has covalent bonding, we can say it really two different ways, that would be a covalent compound, or sometimes books will call it a molecular compound. Okay, these are really equivalent. Okay, it just depends how you want to define it. Okay, but both of these refer to a compound that is composed of two nonmetals. Okay. All right, so for these Lewis structures, you are going to just partner up atoms that bring in so many bonding electrons. Okay, and so hydrogen, as you remember in the previous chapter, we looked at electronic configurations, right? And so we saw the electronic configuration for hydrogen was the easiest, right? It was just 1s1. And so you've got just this electronic configuration. So that means that hydrogen just has one total electron. Okay, so it has one electron total, which means that you have one valence electron. Okay, and so a valence electron, I'm using a lot of quotes today, aren't I? Is the number of electrons that participate in bonding. Okay, and the easy way to figure out how many valence electrons something has is if you look at the periodic table, it'll be whatever group it's in. Okay, so we've got the group 1, the group 2, and then we kind of skip transition metals. Then we've got this block with the 13, group 14, 15, 16, 17, and 18. Okay, so some books will call this the 1A, the 2A, and then you've got 3A, 4A, 5A, 6, 7, and 8. Okay, all with A's here. The Roman numerals actually tell you how many valence electrons. Okay, so if we skip this group, you can have a maximum of 8 valence electrons. Okay, that is if you're in a noble gas, you have 8 valence electrons. Okay, if you're in the group 17, like the halogens, then you have 7 valence electrons. This would have 6, 5, 4, 3, 2, and 1. Okay, so anything in group 1 or the alkali metals will have 1 valence electron. Calcium, magnesium, whatever, would have 2, and so on. Aluminum, all those would have 3 valence electrons. Okay, and so those correspond to the electrons that are farthest from the nucleus. Okay, and so for instance, if we look at boron, remember that configuration was 1s2, 2s2, 2p1. Okay, and so what we're saying is that we really don't care about the 1s electrons because they're too close to the nucleus to interact with another atom. So these are called core electrons. So we only look at the electrons that have the highest n quantum number. Okay, so remember this is n equals 2 as far as quantum numbers. You want to look at the electrons that are in orbitals farthest from the nucleus, so that means the n is the largest value. Okay, and so if you add up these, you will have a total of 3 valence electrons. Okay, and that's in group 13 really, but it's group 3A. Okay? All right, so these are just kind of then overlapping. So fluorine, if you want to do the Lewis dot structure or the electron dot structure for fluorine, fluorine is in group 7A or group 17, so it has 7 valence electrons. You just put the dots around them. Okay, so you would put 7 dots around it. So 1, 2, 3, 4, 5, 6, 7. Okay, and so this is showing now how 2 of those can overlap, right? So you've got 1 unpaired electron here and one here. So you just put them together, and now you've got a bonding electron pair between them. Okay, so this is for F2. Okay, the molecule F2, that would be the Lewis dot structure. And you can also write this as this, just a line. Okay, so both are equivalent. We're just saying that this line can take the place of these two dots. Okay, the Lewis dot structure for boron, just by itself as an atom, if it has 3 valence electrons, you could draw it, I guess, any way you really want. You could draw it like that if you want, but what makes the most sense is kind of like this. Okay, and so that's showing you that it really likes to form 3 bonds with something else. Okay, because it's wanting to partner up this unpaired electron to get one more from something else, like a chlorine, for instance. Okay, so it can partner up with 3 chlorine atoms. Okay, something like this. Okay, and so now these partner up, and we can have something that's called BCl3, or boron trichloride. Okay, all right, so that is where I will end it today. And then what we're going to do tomorrow, we are going to go through a series of steps of what you have to do to draw the Lewis structure for more complicated molecules. Okay, all right, so any questions before we sign off?